Have you seen a complex curve on a graph and thought, how do people figure out exactly where it rises, falls, and changes shape just by looking at an equation? In this video, I'll show you the step-by-step process that transforms these equations into information that will help us sketch curves using differential calculus. We'll follow these steps. First, we'll define the function and locate its zeros. Next, we'll find the first derivative and critical points. After that, the second derivative and inflection points. And lastly, we'll analyze and plot the curve. For this example, we'll be working with the function x cubed minus 3x squared. Firstly, we'll want to find the zeros, the x values where f of x is equal to 0. So what we'll do is we'll set x cubed minus 3x squared equal to 0. And now what you'll notice is that you can take out an x squared, and that'll leave you with x squared times x minus 3. And this gives us two roots, one at 0 and one at 3. The double root, we'll see what that does later. To understand the shape of the graph, where it rises or falls, and how it curves, we need the first and second derivatives. The first derivative will tell us where the function is increasing or decreasing. The second derivative gives insight into the concavity and potential inflection points. Let's calculate the first derivative. The original function is x cubed minus 3x squared. Using power rule, we'll get to 3x squared minus 6x. Now if we set this equal to 0, we can factor out an x, and we'll get 3x times x minus 2. And this will give us the roots of the first derivative. These are called critical points, and they occur when the first derivative is either at 0 or undefined. And they show us where the max curves and minimum curves of the function could be. Now, how do we know whether each critical point is a max or a min? Well, we can test its behavior around the critical point. For 0, we can use -1, which is on the left of 0, and it'll show us that it increases because the first derivative's value is positive before the critical point, and it's negative after the critical point when we test 1, which is to the right of 0. This shows us that the original function increases when it goes up till 0, and then after 0, it starts decreasing. This shows us that x is equal to 0 is a local max. Now, for the next critical point, x equals 2, we can do something similar. So we can test 1 as a point from the left side of 2. And when we plug it in, it's a negative value at the first derivative, which shows decreasing on the original function. And it's positive on its right, which is increasing. We now know x is equal to 2 is a local minimum, because if we start decreasing on the original function, and then we go into increasing, it's kind of like the curve of x squared. It's just the regular parabola shape. Now for the last step, almost. Find the second derivative. And the second derivative of the original function is 6x minus 6. We can set this equal to 0 and solve for x, and we'll get 1. Now, what we can do with this 1, which is called an inflection point, is where the function changes concavity. And concavity is the nature of the curve of the function. Concave down, you can think of as the downward part of the curve of the negative x squared function, or like the downward parabola. And so we can test around this point to determine if it changes from concave down to concave up or vice versa. And here we use 1/2 and 3/2. And it's negative on the left and positive on the right for the second derivative, showing concave down to concave up. So here's all the points that we need to know. 0, 0, which is a local max, 2, -4, which is a local min, and we find this -4 and -2 at the inflection points for the y values by plugging them back into the original function. These are all our points that matter. So when we go to plot the curve, since we know that on the left of 0, it starts increasing, we can draw that it increases up until the point 0, in which it starts decreasing until we hit that inflection point at 1, -2, where it changes concavity and it starts increasing again after the point 2, -4, and reaches 3, which is our last zero. And this will give us a rough estimate of our function.